Now, as we discussed in the last class, hydrogenation is an extremely important process for both academia as well as industry. It allows olefin to convert into alkane. Any unsaturated molecule, to be precise, can be hydrogenated to give the relatively more saturated organic molecule. Now, this has been quite exciting from a number of point of view that we can now prepare complex molecule with the help of a carbon-carbon existing structure or other carbon nitrogen unsaturated molecule or different unsaturated unit that may be present in a molecule. Now, hydrogenation catalyst can be of two types, monohydride and dihydride. As the name suggests, monohydride will have one hydride in it to start with. These are the catalysts, which some of them are shown in here. This rhodium catalyst with hydride and carbon monoxide along with them. It could have triphenyl phosphine, 3 of them. Or it could be something like ruthenium catalyst, where once again one hydride and one chloride along with 3 triphenyl phosphine we can see. Now, the commonality between these two catalysts, simply first point is both of them are having one hydride to start with. Now, this hydride can give us the product in a very quick fashion. For example, if you start with olefin and hydrogen and this monohydride catalyst, we can get this hydrogenated product. Now, let us look at the basic differences between the monohydride catalyst and dihydride catalyst. As I said, monohydride catalyst will have one hydride to start with, right? So the starting material or the starting complex that you would like to have for this sort of catalyst will possess one hydride. Now, this is a complex where H- and rhodium is 1+. What is the electronic configuration of rhodium? Valence electron configuration. This is going to be D7S2 complex, like total 9 electrons. Now, if it is rhodium 1+, this is 8 electron species, right? 8 and hydride 2, 8 plus 2, 10, carbon monoxide 2, 12, 3 triphenyl phosphine, each of them giving 2 electron due to this lone pair of phosphine. So 6 electrons, 6 to 8 plus 8, 16 plus 2, 18. Total, it is an 18 electron complex. Now, as you know, for any 18 electron complex, it is not possible to undergo a direct reaction unless they lose the number of electron. So 18 electron, if it wants to go up, it is going to be 19 or 20 electron, which is not really feasible. So the first stage or first step it has to do is a ligand dissociation. Now, of course, these reactions are interesting to note that between carbon monoxide and triphenyl phosphine, it is the triphenyl phosphine that goes out, one of them, because carbon monoxide is a better ligand, sigma donor as well as pi acceptor, so it will hold on to the metal more tightly. Triphenyl phosphine, on the other hand, can be dissociated, as you can see here, 18 electron species to 16 electron species. Of course, you know this standard way of getting rid of or if you want to lose a particular ligand, there are many ways to lose a particular ligand. In this case, there is a clear need that we need to reach from 18 electron to 16 electron process. Otherwise, the hydrogenation reaction we cannot start with. But for example, if you have a chloride, you want to lose chloride, you can add silver salt, right? Silver chloride will precipitate out. If you have carbon monoxide, you want to lose carbon monoxide, you can photoexcite the molecule at that point where the metal carbonyl stretches, right? So that is another way. If you have an anionic, bulky anionic ligand, you can protonate them, right, to lose that ligand from the structure. There are many different ways by which one can look at losing the ligand from the metal core. Another way is if you have a cationic one, then you include maybe a hydridic species. You add an hydride to get rid of that cationic intermediate or cationic species that is attached with the metal center. So be it halide, so silver salt, be it carbon monoxide, you can use a photosensitization, you can use a cation for an anionic ligand to be removed, for an anion to be a cationic species to remove it. So for example, protonation. In any case, what you see here is this 18 electron to 16 electron species formation is having, wait a minute, it looks like my slide is having issues. Slide is frozen. Hold on for a moment. I'm just coming back in. Okay, so I'm back in. Hopefully it is visible. Okay, so what we are discussing, that this 18 electron to 16 electron species formation can be happening by many different ways. In this case, a simple triphenyl phosphine can be lost, or they are always in equilibrium, so there is an opportunity to lose the triphenyl phosphine. Otherwise, a photo dissociation for CO, or if it is a halide ligand that has to be lost, silver can be added. If it is a cationic species, we can use an cationic counterpart, we can use a anionic one, or if it is an anionic ligand, we can use a cation such as proton to protonate. For example, if you have a tertiary butyl anion or tatamyl one, these are the one you can perhaps protonate it. Nonetheless, so 18 electron to 16 electron species is formed. Now from there, as you can see, you can have the olefin that can coordinate. Why in this case olefin can coordinate? Because it is a 16 electron species, it can go for 18 electron species right away. Subsequently, a beta migratory insertion at this olefin can take place to give you this 16 electrons process. Okay, if you count it, it was a hydride and olefin, two different ligand become one ligand. So that means reduce in electron count by 2. So this is the beta migratory insertion. As you see that at the alpha position, it's the carbon center which is attached with metal, and the beta position hydride is really incorporated. Okay, so this is a beta migratory insertion that is happening over here. From there, an oxidative addition, it is now a 16 electrons process, and oxidative addition can take place to give you 18 electron species, where you see the two hydrogen. It's a concerted type of mechanism that is taking place to give you this rhodium dihydride complex with an alkyl group. Now the question is, how do we know that this hydrogen oxidative addition is concerted? Right? For that, you will see that if you do this reaction in different solvent, there is no net decrease or increase in rate. That means there is no clear generation of charge. That again indicates that it is a concerted mechanism. Okay, there are many different ways you can probe these reactions by choosing a radical scavenger, whether there is a radical process involved in this reaction. That can also you can find out. There are many ways to know that whether this is a concerted oxidative addition or not. As I said, one could be adding radical scavenger. If you add radical scavenger, you will see there is no change in rate of the reaction. If you are doing an oxidative addition in a concerted manner, if there is no solvent effect is found, polar, non-polar solvent, all of them are giving the same rate, once again that tells that oxidative addition is happening in a concerted manner. Subsequently, the reductive elimination between this hydride and this alkyl group takes place to give you the product. Now the valid questions here are, what is the first step? First step has to be ligand dissociation, because without ligand dissociation, it cannot go anywhere else. Now the next question would be, from this 16 electron species, why can't we have this oxidative addition? In other words, can we have oxidative addition over here? Answer to that question is no. If you have oxidative addition, then olefin coordination will lead to a 20 electrons process, because you see oxidative addition has led from 16 electron to 18 electron. If this 16 electron goes to 18 electron after oxidative addition, then where the olefin is going to coordinate. So that is definitely not a viable mechanistic pathway to form the product. So the two most important thing is ligand dissociation has to happen, and number two, olefin coordination has to happen after that. Okay, it's not that oxidative addition will happen immediately after that. If that's happening, that's an unproductive or non-productive pathway, because if after oxidative addition it will be anyway 18 electron species, olefin coordination to the rhodium center will not be feasible. So I hope it is clear why the event has to happen the way it has happened. It's an 18 electron species goes to 16 electron species. These 16 electron species can then go to an 18 electron species upon olefin coordination. Since a monohydride catalyst is there, it can migrate in a beta migratory fashion. Then it comes back to 16 electron sources. If over here oxidative addition into hydrogen was happening, then you could imagine that rhodium trihydride species is forming. Rhodium trihydride, which would have been an 18 electron species. Now what would you do with that 18 electron species? You cannot attach an olefin with that on the 18 electron species. So such an oxidative addition will be unproductive. And this is where I think it is important to understand that this is going to be is oxidative addition at the end. Okay, at the very end oxidative addition occurs for a monohydride catalyst. Of course, another important thing is when it is rhodium alkyl species, then this species is electron rich. The oxidative addition becomes much more feasible compared to the 16 electron species you see to start with here, hydridorhodium carbonyl and phosphine complex, right? So it's all those things put together, we have a situation where oxidative addition happens at the very end, not at the very beginning, and then upon oxidative addition, then beta hydride elimination or reductive elimination in this case can take place. Reductive elimination takes place to give you the hydrogenated product, right? So this hydride and this alkyl group will move. Okay, so we'll move on from this. I hope it is clear why 18 electron to 16 electron transformation was necessary, why hydrogen oxidative addition cannot take place right after this 16 electron species formation. 2-3 reasons are there. One is if it happens, then it reaches to an 18 electron species, and then there is no olefin coordination, so it's not going to be a product forming pathway. This is going to be non-productive pathway. So since this equilibrium, since these reactions are involved with equilibrium, it will eventually not go to that pathway. Another thing is, of course, oxidative addition on this 16 electron complex is not that preferred, because you will have an alkyl species on this 16 electron complex where the oxidative addition is facile, because this complex is more electron rich. It's a nucleophilic one. As I said, this reaction mechanism also going to be concerted in fashion. So we will have a very interesting opportunity to do these reactions in a very efficient manner. Okay. So moving back in, so putting together all these effects meaning right electronic configuration, right understanding of these species is critical for gaining these reaction conditions, as well as to understand when which step is going to happen. So ligand dissociation, the order of this reaction is ligand dissociation, olefin coordination, beta migratory insertion, oxidative addition, and reductive elimination. So this is absolutely what is happening. If it is not, then it becomes difficult or impossible to proceed. One of the exciting thing is intercepting this intermediate is very, very critical or difficult. So far, I mean, it has been really, really difficult to get these intermediates. Okay, moving on, for the dihydride catalyst, we were discussing briefly in the last class. So we have for the dihydride catalyst, we have the Wilkinson catalyst, which is most famous, as you have seen. As well, it has dichloride and bis-triphenyl phosphine ligand. Of course, this is a rhodium 2 complex. Now you have other opportunity. You have other opportunity in there where well, this is little bit wrongly written. So this should be actually one of the phosphine, one chlorine is there, right? So it has to be rhodium plus 1+ ligand system. Anyway, all of them are rhodium 1+ ligand system. 2 phosphine ligands are there, and in this case, this olefin is acting as a sacrificial substrate, because this is a good hydrogenation catalyst. As you would expect, a ligand which has olefin like this and not really a strong chelator will be able to fall off from the metal center very effectively. Stock-Osborne catalyst, OSBORN, Stock-Osborne catalyst is a very, very effective one. Stock-Osborne catalyst for the hydrogenation reaction. For iridium, it is once again the iridium 1+ catalyst, just like rhodium. This is cyclooctadiene or COD. This cyclooctadiene, iridium plus, and PCOI3 pyridine ligand will be known as the Crabtree catalyst. It's very effective for the hydrogenation reaction of the substituted olefin. Both the last two cases, as you see, that these are the one which will be effective for the bulky olefin, because this olefin coordination or the ligand, part of the ligand will fall off for these sort of reactions. right? These are sacrificial ligand. That means enough coordination unsaturation, coordinative unsaturation is present, which will lead to the unsaturated removal of this DG, removal of this ligand, and therefore we will be able to get the reaction at this site, even for the bulky olefin ligand. Of course, each catalyst has its own advantages, right? So this, for example, Wilkinson Catalyst is very cheap and readily available, and but the net cost is also not that high. On the other hand, rhodium Stock-Osborne catalyst or Crabtree's catalyst are relatively expensive catalyst. Now the reaction mechanism, as you have seen, reaction mechanism is going to be first a square planar rhodium complex, right? So this is going to be a rhodium 1 plus, as I said, rhodium 1 plus, it's a square planar complex. Why? Because rhodium itself is D7S2 system. This is 1 plus will be D8 system. D8 system with this ligand, it's going to be square planar, right? Tetrahedral, there is no chance. And then what happens, one of the phosphine ligand has to come off, one of them comes off. From the tris phosphine you have now bisphosphine. This is more of the reactive species. Okay, this is, you can say that starting material in this case, it's not really the one which is really doing the chemistry. It's the reactive species where it loses one of the phosphine arm, and that is when, or this is the one which is doing the chemistry, right? Subsequently, oxidative addition onto the rhodium happens. I would like to remind you that to start with, none of these two rhodium complex has any hydride. If you remember, if you go back, to start with the monohydride catalyst, it started with an hydride. Monohydride catalyst started with a hydride in them. Okay, so hydride is already in there. But with a dihydride catalyst, there is no hydride present to start with, nothing. As you can see, none of the starting materials is having hydride to start with. So this is when oxidative addition into hydrogen becomes very, very critical. So again, concerted oxidative addition takes place here. Remind you that none of these intermediate are crystallographically characterized or even spectroscopically well characterized. So if anybody can do these reactions and can characterize these intermediate, that would be quite interesting. Now you may ask, why would not be possible to characterize these intermediate? Well, this is because this catalytic cycle is very, very effective. So interfering with such a catalytic system is always going to be tough. It never really sits down or take resting state in any other stage that very easily. So therefore, getting a crystal structure or spectroscopic characterization becomes very, very difficult. After oxidative addition, it is the alkene coordination that takes place, okay, and then a hydride transfer onto the olefin to give an opportunity to get the terminal alkyl intermediate, which can then, yeah, hello, yeah, hello. There is some disturbance. Hello. Okay, I think we are experiencing some difficulties here, technical difficulties. Hi, Mamta, can you hear me? I think we are going ahead. Hello, is it okay to go ahead? Okay, so anyway, okay, I'm stopping it for now.